welcome to a new experience of my YouTube, namely my face. I'm Jens, and today we're going to look at my radio control grader, and conveniently I have it right next to me. And yeah, so we're going to go through the grader from the front to the back. I'm also going to point out a little bit about the radio control that I built specifically for this grader, and every now and then I will make some comment about stuff that hasn't worked, but mainly we're going to focus on the stuff that you see here, and maybe one or two things that I want to improve further on. If you're really interested in the detail build blog with all the things that did not work in the end, I will post a link to my Flickr account where you can see pretty much every step documented. Okay, so I would say I pick up the camera and then we're going to get right into it. The first function is the front plate. Very simple design, just a piece of aluminium with a little bit of a bend at the bottom, and then I found out that I actually used quite a bit, so I added this strip on the top and on the side to create a little bit more volume to the blade. Simple 30mm by 30mm aluminium profile with a servo inside. Quite a space-saving configuration, and it works really well. So there's not a lot of load to it. Problem is that the servo needs to support the weight of the front blade all the time. Maybe I will add a spring later, but it's to save a little bit of energy in helping the servo to support the load. But for the time being, it works really well. You can also see here that I had to do this pretty ugly but functional design so that the wheels do not interfere in any situation with the lever arm that lifts and lowers the front blade. So, and after the very simple front blade, we come to one of the most complex sub-assemblies of the grader. So one thing that I think makes this grader special is that it's 6x6, so all wheels are driven. And also, when I started with the grader, my plan was to recreate all the standard functions of a modern motor grader. So that means 6x6, which is optional on most graders, but I really wanted to have that. 6x6, steering, obviously, and tilting, leaning of the front wheels, I should say. So, and at the same time, I wanted to use relatively simple manufacturing methods for the grader and not spend a fortune. So, as you can see here, we have a reduced height servo, and we have a standard height servo here. So this one is a Zavux high quality servo. I realized, and it does the wheel lean, and I realized that the weaker servos that I tried before were not up to the stress. Because if you're leaning the grader, you can see here the weight tries to force back the servo. So if you're leaning the wheels, the servo has to work against the mass or the weight of the machine. And yeah, actually, maybe now is a good point to discuss. So the servos, they have a lot of power. If you really break it down, there's a lot of power inside a very small package. But this power typically is mostly in the speed and not in the torque. And what we want to have in many earth-moving models is actually torque. We're not so much concerned about the speed. So, for example, I would gladly have this be a factor of 5 slower and a factor of 5 stronger. But these options do not really exist in the servo market. So, and then it becomes a compromise between, do I build it myself, or do I take a servo and that is a little bit oversized in power, but I need the torque and I don't need the speed, so I buy a servo that is somewhat too strong, but I save the time to build it myself. And in this case I went with a high quality servo, as I said, from Zaworks. Really happy with it, has not failed me yet. And then I have a standard servo here which does the steering, and yeah, all is pivoting as you would expect from a real grader, so that you can always maintain contact with the ground with all 6 wheels. As you can see from the bent rod here, let's zoom in a little bit. So the bent rod here, the bent rod here, and the arrangement of the 2 servos, it was really complicated to get everything in here. Could have gone a bit larger, but this subassembly is already quite a bit larger than a real machine, so I didn't want to compromise the appearance too much. Okay, so here we are. This time the left front wheel, just to give you an orientation where we are in the machine, and I'm zooming in, and you can see that I'm using quite odd wheels. And if you're familiar with the short course truck, like the Traxxas Slash, you will probably realize where this is from. Initially I used stock Traxxas Slash rims, and they worked fine, but then I found these DE racing rims, and they have 2 advantages. They use 17mm hexes, so I can mount them using a standard adapter directly to the motor shaft. Much easier than what I did before, where I had to drill the motor shaft, a bit of a nightmare. And also they have offset that makes the whole track more narrow, so I had more space to get in the motors. And you can see here I think the only green bit on the grader, these are slot car racing motors, which I have adapted to a rather narrow width, or narrow length, or short length I should say, gear motor from eBay. The original motor was very short, so it fitted nicely into this black mounting bracket that I made from polyacetal, but it was just not powerful enough. I realized that having more power on the front wheel is actually really beneficial, and that motor just didn't deliver it. So these slot car motors are actually overkill. They are relatively affordable. Ideally I would like to have something in between, just to make the grader more balanced, but for the time being these work really well. And if you're ever in a situation where you need a lot of power in a small space, and you can afford to pay 10 or 20 quid and some modification time, I should say, it's £15. I think they cost £15 each, 1.5. So yeah, quite doable for the performance that you get. So, and also this large diameter allowed me to put some of the steering mechanism inside the rim. It's not very realistic, of course. Real machines don't have this large diameter on the inside, but functionally they work really well. And the tires, they still are pliable enough to give good traction. I should say that underneath these rubber tires I have weights, so to get the weight higher and the traction better, and yeah, that works quite well. So as you can see, when I grab the tire, it moves quite nicely. I have had some problems with the wires breaking off because initially I didn't solder them well enough. Fingers crossed. That should be fixed now, but that's one of the points that I would like to improve in a later iteration. As you can see, the black part is still designed for a different motor. Now I have a motor that is slightly longer but smaller in diameter, so I think I could improve this, especially regarding the cable routing, so that the cable doesn't interfere with the tires and the steering. And I'll try to show the leaning again. So you can see that this C shape here tilts around this little pivot point, and it's only a few degrees, but it helps to stabilize the machine against the blade side force. And I think that's all to say about the front end. Obviously, you'll see that I have installed lights. I'm not going to point out each of the lights that I have installed. I installed them for a specific meeting in Germany, and I initially didn't really want to do it because it was so much work to route the cables. But I'm so glad that I did. If you go back through my videos on YouTube, you will see that I'm working with this machine in basically complete darkness, and the lights are sufficient for me to work, even if it is really, really dark. Okay, so obviously the mouldboard is probably the part that makes the grader a grader. And there are a lot of functions concentrated in a small room, well, we're just going to go through them one by one. So this motor over a worm gear transmission that I built myself drives this white polyacetal wheel, and you can see that I use the square aluminium piece as a to transmit the torque. Inside here there are two narrow width ball bearings, sealed ball bearings I should say, and well, it works quite well. This is 200 RPM, but of course quite a huge gear reduction. And I initially had, this is the third iteration of circle drive motors that I have used, but finally I'm happy with the torque and the speed. Yeah, so if I move the camera a little bit differently. So we're going to discuss the blade lifts in a bit more detail, but obviously these provide the lifting and roll of the mouldboard. This little motor here, which is able to pivot around these points here, it changes the angle of attack of the blade. And if you can't really see how that works, well, we have another self-built gearbox inside here, and there is a spindle drive. So this, if we zoom in, you can see the brass M4 thread that moves the mouldboard. So again,
here we are, mouldboard, and under these sand or mud protectors we have the end of the threaded rod moving the whole assembly around this pivoting axis here. And also what you can see is this motor, which moves the whole mouldboard left and right. Again, this was quite difficult to get right. So what I'm using now is this motor, which has a basically a winch, and I'm using a fishing line connected to the left and the right, and that works really quite well. You can see here I have an aluminium guide, and then I have plastic or an aluminium track and plastic guides underneath this dust protector here. So the white thing here is the plastic part, and it creates a channel in which the aluminium can slide left and right. So, and this motor gets, if I change the angle of attack of the mouldboard, the whole motor and the guide pivots forwards and backwards. And tilting the mouldboard, changing its angle of attack, that governs how aggressively your blade will go into the ground, whether you're cutting into the ground or you're just rolling the material along. Okay, so that's one function, two functions, three functions, and that governs the position of the mouldboard. So we just looked at the functions that control the blade on this, with regards to the circle, and then we have another set of functions that control the position of the circle with regards to the machine. And so we have blade lift on one side, blade lift on the other side, and then a little bit hidden behind we have another spindle drive. It's a dual telescope, so we have threaded rods that go right, and one threaded rod that goes right and one threaded rod that goes left, thereby saving space and allowing enough lateral movement so that I can position the circle outside of the center line of the machine. Yeah, those are the basic functions for the mouldboard, but I have implemented another function that you can see here. This is a floating mechanism. So on real machines, or I should say on full-size machines, these functions nowadays are all hydraulic, and so the hydraulic valve has an additional position in which it floats. So that means that it's not driven with hydraulic oil from the pump. Rather, the terrain allows a relatively free motion of the blade. So the blade sits on the ground, and the terrain dictates the movement of the mouldboard. And obviously my grader is electromechanical, and I want to have a way to have the same functionality because it's really useful. You will see it in my grader videos. You just drop the blade into floating mode, and you do a quick pass around the sand pit, and the worst hills and troughs will be gone, and you can work without the float and really shaping the terrain in the sense, in the direction that you need. So I'm using two 9-gram servos, and what is inside here is a clamp. You can see that these rods are threaded, They don't turn, but these clamps, the threads serve as a way to secure the clamping. I have again different versions that worked more or less, but it was a problem to get enough force without burning out the motor of the servo. Probably not the motor, rather the electronics. But yeah, I killed a few servos with previous variations. And finally I settled on something that uses a spring. You can see, if you look closely, there is a spring here. So the spring creates the clamping force, and then the servo opens it. And of course now the servo needs to work against the spring, but I arranged it so that it uses a cam mechanism, so that the servo does not see torque either when clamping or when floating. So that is really useful because, as you know, these servos really are powerful, but they don't like to be powered continuously. Then the heat is just going to eventually, at least on these cheap servos, going to melt something. Okay, talking about small servos, here's another one. What this one does is it pulls out a locking mechanism, and then when that is pulled out, it allows the whole saddle to rotate around the center line of this front part of the frame. It's a function that I rarely use. It works okay. Ideally, I would like, as you can see, there's a bit of play in here, and it's probably less than a degree or maybe a degree, but over the dimensions of the mold board, it adds up to several millimeters, and it's a little bit annoying. So I'm thinking of doing that in a more sturdy fashion. Anyway, if this is unlocked, this can freely rotate, and just like the real machine, this is not powered. This is driven or moved by extending the main lift cylinders and basically pushing down on the ground, and then the force is transferred into a torque that makes it rotate one way or the other. Okay, we're making our way towards the center of the machine. So you see another one of these white polyacetal gears, and what you can't see inside, I have a worm drive gear motor, which I upgraded from the original version, again with a slightly stronger motor, not slot car motor strong, but quite a bit of punch, and that really has improved the maneuverability of the grader immensely. It was one of the things that I really needed to address when I was redesigning the whole rear part of the machine. I wanted to have a sturdy articulation drive, and I think I now have found it. As you can imagine, the machine, it's I think 800 millimeters long, 32 inches. It works really well. I have bearings in here, and so both here and there. I have bearings, both radial bearings and axial bearings, or thrust bearings, as you sometimes call them. Very little play, very powerful, very fast. So I can mix the articulation and the front wheels either so that I drive parallel but with the front and rear offset to the sides, or I can drive in a way that really reduces the turning radius and makes even this large machine really maneuverable. Okay, so we're almost at the end. As you can see, I have integrated on off switches, one switch for the radio, another switch for the light. This is where my Turnigy 9X receivers poke into the world, and I'm running standard nickel metal hydride batteries, 12 volts to be precise, and they sit here between those body posts that I converted, or that I use from RC racing. Okay, and what else can you see? Well, you see the bogies or tandems. So yeah, I know the terminology is sometimes a little bit different. If you're doing forestry, you call them bogies. If you're doing graders, they're usually called tandem. Either way, they allow this type of articulation. But you can see that I have these strange levers here that allow another degree of freedom. And these are torque-balanced bogies, something that, well, happens in different industries. If you're into aircraft, into aviation, then you probably know something similar in the brake systems of large airliners. Okay, so in this view, I'm going to try to explain what the reason behind that is. When I did my first implementation without these levers, where I just had the motors inside the tandems, I noticed that it was always the front wheel that was slipping first when driving forwards, or the back wheel when I was driving backwards. Well, the reason for that is quite understandable. If you want to drive forwards, then you have torque in this direction, and much like what you see in a wheelies in a motorbike, if you're revving your motorbike, the front will lift and you will drive on the rear. And just because this wheel is also driven, in contrast to a motorcycle, that doesn't change these physics. So you will always have a little bit. You're not going to do a wheelie, but you will have weight transfer from this wheel to this wheel. And that means that this wheel is more highly loaded and less likely to slip at the same speed setting of your ESC, electronic speed controller. So you can go back into my older videos and see that I did a prototype. It has become a relatively complex assembly, but still doable with only basic tools. And it works really quite well, I have to say. Of course, there's a little bit of friction here, but if you go through my videos, you will see that this old problem doesn't really occur anymore. So I think it was worth doing that. And if you're ever in a position to build a machine with these tandems with integrated wheel motors, so the motors are sitting inside here, maybe you want to give it a try and see whether it works for you as well. Okay, last but not least, the rear of the machine, the ripper or scarifier, depending on where you are, you might call it differently, Similar in idea to the front blade, I have another bit of 30 by 30 millimeters of aluminium, and inside there is a servo. In contrast to the front blade, I have integrated a servo saver here, which I stiffened up with this zip tie, and I manufactured out of aluminium these teeth. They work reasonably well. Of course, the machine, well, it weighs nearly 10 kilograms, has quite a bit of weight and therefore pulling power, so you can indeed loosen, I don't know, topsoil or definitely hard-packed sand, and then loosen it up so that the blade can actually move the material. Okay, as the final thing to discuss, I thought it might be interesting to discuss my radio, or maybe I should say radios, because as you can see I have not one but two Turnigy 9X. Now this is the original 9X. It's running the original firmware. I thought about upgrading to custom firmware. As you know, there are several options, but the reason I haven't done that is that for the time being I can do what I need to. There are some custom functions that ultimately I would like to implement, and then one of the more modern radios or a do-it-yourself version with Arduinos and the NRF24 modules would be possible. But yeah, it allows me a lot of mixing functions, and it works really quite well. So as you can see, I have these joysticks. I have removed the gimbals or sticks from this machine, and these gimbals only have this function. They are dead for the horizontal motion. So so I have taken these out, cut the cables, and spliced in these joysticks. People generally tend to think this is ridiculously complicated, but it's really quite easy to do. As long as your joystick has potentiometers and not Hall sensors, you're pretty much good to go. There are some issues that can arise if these joysticks are not completely centered, or centered in a different way than what the radio expects, but luckily that was fine for me. And what is nice about these joysticks is that they are 3 axes. So I have the 1 axis and the 2 axes, so that is, as you know, from these sticks. But then I also have rotation. And again, I was heavily inspired by Caterpillar. Of course, all other manufacturers also have highly integrated joysticks controls nowadays, but this looks and feels quite similar to the joystick methods, or the joystick design that Caterpillar introduced with the M-series graders. But obviously, this is not a full-size machine, so I don't have pedals. Of course, I know other people have pedals on their radio transmitters, but I have this trigger here for forwards and backwards. Looks a bit flimsy, but works really well. Yeah, and that brings me to the next point. As you can imagine, These joysticks are for flight simulators on the computer. They are not designed for graders, so they had a lot of buttons that I don't need, and they didn't have enough potentiometers or joysticks that I did need. So I've put in these little, let's try to zoom in. So these are, they are commonly called PlayStation joysticks, but of course they are not only found in PlayStation controllers, and I think nowadays actually the PlayStation controllers use quite different means of input. But yeah, if you buy them, stay away from the very, very cheap ones and maybe pay a little bit more. You will have much better neutral and less dead bend around neutral. This is blade lift left, blade lift right. Steering left, steering right. This is backwards and this is forwards. This is wheel lean right and wheel lean left. This and this are the switches for the floating mechanism, and this function is currently dead. It should be the articulation if we are following Caterpillar's convention. Instead I have moved the articulation over to this sliding potentiometer. The reason why I have removed the function for articulation from this and moved it over here is to facilitate the mixing. And I have, with this switch here, I have 3 steering modes. I can either have no mixing, so this one steers only the front, and this here only articulates the frame. Or I can have them work in the same direction, so that I'm doing a kind of crab steer, which is useful, for example, if you're backfilling ditches or doing ditch maintenance with a grader. And I can also work them in a way that they both turn in one direction, and thereby reducing the turning radius. So if I want to do this, quite obviously, if I want to do the crab steer, I want to say I want to use the articulation input, and then the front should just do exactly the same, just in the other direction, so that the 2 wheels stay parallel and I can just go forward, but with an offset, right? So for that to work, and similar for the reduced turning radius, the transmitter needs to know the positions. And then it can say, well, a position of -1 on the articulation corresponds to a position of -1 on the front for the one mode and +1 for the other mode, or maybe 0.7 or 0.9. It's just for comparison. So, if I were to use this input, as you can see, it tries to return to neutral. So if I want to do crab steer, I would have to hold it in this articulated position. And I found that just too annoying for the time being. So it would be nice to have something here that, if I do this, it increases the articulation angle by a certain amount. So basically, to make this this input no longer proportional to an angle at the articulation, but is speed, an articulation speed. However, this radio with its current firmware is not able to do mixing then. This would need a rather complicated script with, for example, the Tyrannus radio, where you have the ability to install complex programming scripts. So that is maybe something that I want to do in the future. Where I have a similar function, but not in the transmitter, rather in the machine, is the lift. So these lifts are actually, the position of the joystick is proportional to the lifting speed. So wherever I am, if I let go of these levers, joysticks I should say, wherever I leave these joysticks and they return to neutral, and that corresponds to the servos stopping their motion. And so that makes working quite nice. It is very similar to how real hydraulic machines work, because on hydraulic valves your lever movement is also corresponding to the velocity of your hydraulic cylinder and not its position. At least on traditional hydraulics. Nowadays, with electrohydraulics and sensors and microcontrollers, you can of course pretty much do what you want. Okay, so we talked through all of the functions on this, and on that side we have talked about of course the blade lift. Left and right moves the mouldboard, left and right, and then this one controls the steering mode, and this one is another of these little PlayStation joysticks. This forward motion changes the angle of attack, and this motion here moves the whole circle left and right by using this spindle drive. Okay, there's another mini joystick here, but it's not in use, so we don't need to talk about it. And then I have on the back here, on one of those knobs, I have the servo that controls the locking of the saddle. It's a function that I rarely use, so it would be, ideally it would be somewhere where I can reach it more easily, but you only really need it if you move the mouldboard into extreme positions, and frankly I barely use that. But as I said, one of the ideas was that I want to have as many of the functions of the real machine implemented in the model as well, and so yeah, that's where it went. Yeah, and I think that leaves only one function, namely this one, and as you probably can guess, there's only one more turning function in the machine, and that is the circle drive. Yeah, and then this controls the front blade, and this controls the scarifier. As you can see, I'm using the flight sticks that have no return spring. So again, this position is corresponding to the servo position. So no hydraulic mode, so to say, on these levers. Yeah, they are both switched on with the same power switch, and I have a little bit of a light there. Again, it's not very high tech. The more modern radios, even the affordable successors to the Turnigy 9X, have backlit displays, and obviously that makes working in the dark much easier, but during normal operation I barely ever have to go into the menus of the controllers, transmitters, to change settings, and if that really is a necessity, then I have this little LED light to help me find my way. And yeah, with that said, I think we're done. So there you have it. My roughly 1/14 scale 6x6 motor grader from front to back. Thank you very much for watching. Until next time.